So for water entropy, water that is free, that is not sort of anywhere near a hydrophobic group, can orient itself 6 different ways. Okay? It has a multiplicity of 6 because it's in a tetrahedron with other water molecules, and it can kind of arrange itself in 6 different configurations. I can pop that up. So this looks like this here. Okay? So all the different ways a single water can be dependent on when it's making 4 H bonds with other water. But when there's hydrophobic groups exposed, such as in the unfolded protein case, 2 waters will be sort of held in a particular position relative to all of those H groups. They act as sort of a cage or a shell. They're kind of stuck in a configuration that is not as entropically favorable. But when the protein folds up, all of the hydrophobic groups can make interactions with each other, and all of this water is essentially free to H bond with other water again. Okay? So there's some approximations for water's entropy. We estimate that 2 waters get trapped on every hydrophobic residue. This is another assumption that half of the residues are hydrophobic. Again, for a globular protein, if we're saying about half of them go to the interior and the other half are on the exterior to interact with water. So then the number of waters that would be affected would be 2 times the number of residues, but we're saying only half of them are hydrophobic, so make it nice and easy. The number of waters affected is the same number as the length of the overall protein, or N sub res. And again, bulk water, when our protein is folded, has 6 possible states it could be in, or a multiplicity of 6, whereas restricted water in the unfolded state has multiplicity of only 2. Okay, so this is a reduced entropy when the water is sort of trapped in this sort of caged or shell configuration around the hydrophobic stuff. Okay? So here is an entropic calculation just for water. That's what the W subscript is indicating. So unfolded protein case, the water entropy would be gas constant times 50 is the number of waters affected, times the natural log of 2. This was the multiplicity for each water. This is the entropy for water when a protein is folded. Now we have gas constant times 50. This is the number of waters affected, and the multiplicity went up. It's now the natural log of 6, different ways it can be oriented. So if you want to get the change in entropy of water when you fold the protein, take the entropy of water in the folded case, this is final, minus the entropy of water in the unfolded case, this is initial. This would be 50 times R times the natural log of 6 minus the natural log of 2. So here we have a positive change in entropy for the water when I fold up my protein. And again, like I said, this is the water being freed. Okay? I don't care so much that you have the exact numbers down, so much as understanding conceptually what's happening with the water, and that it has a much bigger positive change in entropy to sort of outweigh what's going on with the protein itself. Okay? So if you put it all together, the enthalpy of water is not further affected. What this is saying is that the enthalpy of the water was already encapsulated in the enthalpy change of the protein. Okay? So we have no additional enthalpy determination with water. We just have a change in delta G as a result of the entropy change of the water. Free energy is additive, so we have a total free energy change would be the change in free energy of the water, the change in free energy of the protein. We had a positive 73 from before. This is negative 137 kilojoules per mole, so now it's spontaneous, just as we expected. Okay? For a 50 residue, single unit protein at T equals 300 Kelvin, protein folding is favorable because of the hydrophobic effect. This is a nice YouTube video, it's 14 minutes long, that covers hydrophobic effect and covers the sign of delta H, delta S, delta G for this case. If you haven't watched it, I recommend watching it. I like the woman that does it. I think she does it well. Okay? So hydrophobic effect is essentially the fact that entropy increase of water is the driving force for protein folding. And again, the signs of these terms, delta S, delta H, and delta G, for a folding reaction will be different depending on whether you've considered just proteins, just water, or proteins and